Good afternoon, everyone. Welcome to this BSI webinar, Future of Vehicle Safety, ADAS to Automated Driving. Thank you for joining. My name is Nick Fleming, Associate Director, Transport and Mobility at BSI. I'll shortly be handing over to our chair for today's event. But before I do that, I just wanted to make a few comments and run through the obligatory technical housekeeping for the event. So this is a listen-only webinar that is being recorded. We want that. What that means is you won't be able to unmute yourselves or turn your camera on. Only our speakers, panelists will be able to do that. But we do want the session to be interactive, so we welcome your questions via the Q&A function that you should be able to see in the right-hand sidebar. There's a drop down there, and you can submit any questions during the webinar, and we'll try and pick them up in the short Q&A session we'll hold towards the end of the webinar. And we'll try and leave a good amount of time for questions there, because I'm sure there'll be lots of questions. If you experience technical difficulties, again, you can submit any questions there, and our conferences team will look at that and try and help you. On completion of the feedback survey that we'll send following the event, you'll be able to access a recording of the webinar if you wish to. And also, we wanted just to flag up, this is a CPD recognised webinar, so please request your certificate via the feedback survey following the webinar. If we can move on, please, Andrew. So we've got a fantastic range of speakers today, and I think for me, our vehicles are becoming increasingly sophisticated with onboard technologies. Most new cars will have some form of advanced driver assistance system or safety feature, and many of these features are perhaps not a world away from what we would consider partially or conditional automated driving. And in the coming years, we anticipate seeing more automation and self-driving vehicles on our roads and off our roads. So how is this actually going to take place? To some extent, the more we look at how we bring self-driving vehicles and technologies to our roads, the more it illustrates how incredible human drivers can be. Our perception, decision making, awareness of our environment, and ability to anticipate hazards and risks. I say can because we also recognise that such features and systems equally have the potential to remove driver error and reduce driver error in collisions and road accidents, which is something we want to do. But that only works if the technology is safe and secure. And there are other benefits too, potentially from automated vehicles, ranging from improved social inclusion to productivity. So it's about getting the balance right, and how do we manage the introduction of these technologies and unlock these benefits? What are the current emerging concepts, techniques and tools, standards and regulations to support this transition from ADAS to automated driving? At BSI, we, through our technical committees and work as a member of standards organisations such as ISO, we are now seeing the first international standards emerging to help enable testing and operation of automated vehicles, along with more established engineering concepts such as functional safety and SOTIF, which we'll hear about a bit later. We've also been working closely with UK Government's Centre for Connected and Autonomous Vehicles and Industry to develop our own standards to support organisations involved in automated vehicle trials and development, to help them manage operational safety. We've developed common language, taxonomies and vocabularies to promote consistency. The work we're doing with CCAV now looks towards advanced trials and deployment, and we'll hear again more on that during this webinar. So to help us talk across all of these points, we have an expert panel from across industry, academia, and those directly involved in BSI's standards work, and that includes Edith Holland from Hariba Myra, Prashanth Jirachi from WAVE, Siddhartha Kastegir from University of Warwick, WMG, Paul Spence from PKS Insights, and Brian Wong from Burgess Salmon, the law firm. and I'm because this is such a complex area with so many moving parts. I'm pleased and I must say slightly relieved to be handing over to Professor John McDermott, OBE, to help chair today's webinar for us. As well as being Professor of Software Engineering at the University of York, John is also Director of the Lloyd's Register Foundation Assuring Autonomy International Programme, focusing on safety of robotics and autonomous systems. John has been an advisor to government and industry for several decades on these types of matters. He is a fellow of the Royal Academy of Engineering and a non-exec director at Health and Safety Executive. Importantly for today, John has also been the chair of BSI's CAV Standards Advisory Board since 2018. And this was set up to help guide the BSI standards program I just alluded to, supported by UK government, CCAV, DFT, and developed with Innovate UK. I'll hand over to John now for his remote opening remarks and to guide us through the rest of the webinar into the Q&A. So thank you very much, John.
Nick, thank you very much for that kind introduction. I hope everybody can hear me and I can also make the slides progress. Let me try again. We're going to talk about the future of vehicle safety, in particular the transition from automated driver assistance systems, or ADAS, to automated driving. I think everybody will agree that this has the potential to improve road safety, but to realize that potential, we have to address and solve a number of challenges. There are many of those highlight here too: the need to address the safety of the intended function, which is something we'll hear quite a bit about this afternoon, but also we need to consider safety through life, including the time that the system is in use. It says here these are major changes in emphasis. These are not entirely new, of course, but actually the levels of autonomy we're talking about bring those really to the fore, and we can't ignore them. The discussion today is going to end up with a presentation about some of the potential legal changes around autonomous driving on the UK roads, and that's very much the background or the context for our discussion today. We're here considering safety and standards. As already mentioned, there are challenges around assuring safety. Two specific ones are identifying how safe is safe enough. Is this as safe as a human driver, or are we going to introduce concepts such as ALARP and so on? And having chosen that, how do we go about measuring it? Through ISO 26262 and through practices in other industries, it's become quite common to develop safety cases. If we're going to do that for an automated driving vehicle or a system, what is sufficient evidence? What's the right sort of evidence to have to support that safety case? These are difficult questions which don't have a very clear answer, although I hope we will shed some light on them today. But also, standards have an important role to play. Standards are established by consensus, and they give us rules and guidelines and also characterize activities and the results of these activities that help us in addressing these challenges. And actually, by removing uncertainty in what's a complex area, it helps industry to work efficiently. It gives a way of having better interaction between industry and regulators. Industry know what's expected, and also regulators know what they can expect to receive from industry. And my expectation is that the regulations we will have around autonomous driving will be quite abstract, will be quite simple. These standards can also provide the technical underpinning to make these regulations make sense and have practical force. I've already mentioned there's a legal context here. There's currently a government consultation on the connected and automated mobility. I won't read all of this quote, but it talks here about specifications and standards, and the bit highlighted at the bottom, particularly relevant for technologies such as self-driving that are developing rapidly. So it's emphasizing the importance of standards, but you might say, hey, technology is developing rapidly, but standards normally evolve very slowly. I'm well aware of some, like 61508, that took more than a decade for the first edition to come out. So what do we do about that? Well, this is where some of the BSI activities, which I've been, fortunate enough to chair the steering committee for the last few years, I think really come to the fore. So the BSI has been doing work in this area, trying to be much more agile than is normally the case in developing specifications. So some good practice documentations, for example, publicly available specifications and flex standards being produced that can be drafted quickly and actually can evolve and change as ideas industry matures. These documents can then inform the wider standards community. Although we're focused here perhaps on the BSI activities, the intention is that we can learn from this experience and influence others, ISO, SAE, etc., in the work that they're doing. And this is very much evidenced and supported by the fact that some of the paths that have been developed so far have been downloaded in sort of 50 different countries around the world. The standards also had substantial input from industry, who've both helped to develop and to review individual paths, and in providing oversight. And I'm very grateful for the input I've had from industry in the panel that I chair. And so on to the objectives for this afternoon. What I hope is that the attendees here will get a better understanding of current initiatives relating to the introduction of automated driving in the UK, particularly with a focus on safety and assurance. Also should help attendees to understand the role of standards in that context, and also the relationship between standards and the regulatory framework. I've already mentioned that we will have a focus on SOTIF. In fact, that's where we will turn first to understand about this new standard that's looking at how we assess the safety of the intended function, and also have a very interesting perspective on the use of operational data for safety assurance. Again, as I mentioned earlier, I think we have to focus more on in-use issues now than we did hitherto. And overall, I hope this will help the BSI to understand current concerns that relate to automated driving, where they might focus some more of their effort in the future work on standards. So that was all I wanted to say by way of introduction. It now falls to me to introduce the first speaker. I'm delighted to welcome Edith Holland. Edith's Chief Engineer for Functional Safety at Hariba Myra. I'm responsible there for planning, technical governance, and delivery of customer functional safety and SOTIF projects, development of functional safety processes, and training. She's one of the UK experts involved in developing ISO 26262 and ISO 21448, the SOTIF standard. And prior to joining Hariba Myra, Edith worked as a functional safety engineer at Jaguar Land Rover. So very broad experience that's relevant here. Today, she's going to be talking about the core concepts behind SOTIF and the ISO standard 21448, and we'll explain a bit more about how this might be put into practice by those developing vehicles with active safety features and possibly automated driving systems such as ALKS. Edith, over to you.
Thank you, John, and hello and welcome to everyone. All right. So I will be starting this webinar with a short introduction, as John said, to the topics of functional safety and SOTIF, and also talk about the differences and commonalities that exist between them. We'll also look very briefly, of course, in the time available, at the two ISO standards, and they've been mentioned a number of times already, ISO 26262 and ISO 21448. And then while I talk about this in theory, I'll hand you over to Prashant afterwards, who will talk about applying the requirements from the SOTIF standard in practice. Functional safety as an engineering discipline came into the automotive industry somewhat a bit later than other industries, but when the development of vehicles moved from being mainly purely mechanical systems to increasingly complex software-based electronic systems like ABS or stability control systems initially, it was found that if those are not functioning correctly, obviously you could have hazards that need addressing. And that's why we now have ISO 26262, or have had ISO 26262, sorry, I should say, as a standard for functional safety for over a decade now. But technological advances haven't stopped, as we heard, and the automotive industry is still busy working on making cars safer. And one of the avenues that's pursued is obviously removing the human driver, as they are, as per the road traffic statistics, the cause of most accidents. As a result, we've got even more complex electrical software-based systems. We've now got lane keeping systems, highway assist systems, automated parking systems, those types of systems. And we're adding these new software-based systems that have got even more complex technologies, new sensor technologies like LiDARs, or new types of software algorithms like machine learning. For those types of systems, it's more difficult still to ensure that they operate correctly, and John has hinted at that already. And safety assurance methods have to adapt accordingly. And one of those, of course, is safety of the intended functionality, or SOTIF. And we've now got the new full standard ISO 21448, and that aims to provide a systematic framework that enables engineers to identify and reason about risk associated with these types of systems. Possibly also worthwhile mentioning at this point, we talked about legislative aspects as well, and both ISO 26262 and 21448 have been picked up and made part of regulatory frameworks that are being put in place for more complex automotive systems as well now. So their benefits are being seen. Yeah, while my presentation today, as John said, is focusing on safety of the intended functionality and to a lesser extent functional safety, as that's wider known, it's also worthwhile, obviously, that mentioning that there are other aspects of product safety and particularly operational safety, and we're getting a bit of an overlap, as we see later on when we look at the process in more detail. But for now, let's start with a little bit of background first by looking at ISO 26262. So this is the functional safety standard, which gives guidance on how to avoid or reduce risk due to malfunctioning behavior of EE systems. And here we see the functional safety, the hazard, the model behind ISO 26262. So these malfunctions arise from faults in the EE systems, and they cause a hazard, which is what ISO 26262 is aiming to address with its guidance. Engineers would perform a risk assessment, and that's what this slide is trying to show as well. So we're looking at risk as a combination of severity of potential harm that could result from a hazardous event, in combination with the likelihood of the operational situation and the controllability of that situation. And then based on this risk assessment, ISO 26262 sets out requirements that ensure that the malfunctioning behavior is addressed in order to able to argue that unreasonable risk has been avoided. Hopefully, hazards due to malfunctioning behavior and overall concepts of fault and failures are something engineers are more familiar with. So let's move on straight away and look at the difference or the model behind 21448. You can hopefully see in comparison this model looks a bit more complex straight away. First of all, we've got the definition here. So the standard, the SOTIF standard gives guidance on how to reduce risk from functional insufficiencies instead of hazards caused by malfunctioning behavior. So instead, we're looking at hazardous behavior that is caused by a triggering condition. And that is a condition that is present in the environment that the vehicle is operating in, and that the functionality is not able to or insufficiently able to handle. So a triggering condition stimulates a functional insufficiency in the system. And this might be both at system level or element level. So we're still talking or using concepts that we've got in ISO 26262, although we don't use the word item in 21448. So we talk about vehicle system level or element, which is more akin to the component level in 26262. And it's this, so yes, it's this functional insufficiency that can activate hazardous behavior, either hazardous behavior directly at the vehicle level, or we also need to consider functional insufficiencies that can negatively influence the controllability of a hazardous event. So that's at the bottom of the slide. We also have to consider misuse in SOTIF, and we distinguish between two separate types of misuse. So misuse can either be a triggering condition, so an instigator of potentially hazardous behavior, and then we consider that, or we call this direct misuse. And then we also have indirect misuse, which is a factor that can influence the controllability, and that's when there's functionality designed to improve controllability, and then we can argue about or reason about insufficiencies of that functionality. The key difference, really, hopefully to take away from these two models, is how in SOTIF the environmental contribution to the hazard is regarded compared to ISO 26262. So in SOTIF, it's always a combination of something within the system and the outside world that results in the hazardous behavior, unlike 26262, where the root cause only comes from within the system. Right, then moving on. So here on this slide, we've got in a very short summary of the guidance in ISO 26262. As we saw, the overall aim of functional safety activities is that unacceptable risk due to malfunctions of a vehicle function in an EE system must be prevented. And how do we go about this? We usually distinguish between two types of measures. We can put measures in place that prevent errors from occurring in the first place by proactively implementing a safety management process and performing safety activities alongside engineering development activities, with the aim to ensure that a design is free from systematic design errors. But then secondly, because we also have to accept that no system or no design will ever be 100% free from faults across its lifetime, we also need to consider error control measures. That means ensuring the technical design solutions are capable of controlling faults when they occur. And together, these measures, as I say, intend to result in a reduction of risk from an unacceptable level to an acceptable level. which of the measures in ISO 26262 apply to a particular function is, of course, dependent on the ASIL that is determined during risk assessment. Excuse me. Coming back to SOTIF, the overall aim of SOTIF is, of course, also to reduce risk, but the approach differs from what is set out in ISO 26262. So instead of safety requirements addressing faults, the overall aim in SOTIF is to identify sufficient triggering conditions, so the causes of the hazard, and address them by specifying SOTIF measures and setting criteria for acceptable risk of the intended functionality. There is no concept of SOTIF requirements, so not like we've got in ISO 26262 with safety goals, functional technical safety requirements. Basically, SOTIF measures means that the specification of the intended functionality is continuously modified and improved to align to its operational design domain and the conditions that are within the operational design domain. And so that's either done through changes to the specification of vehicle or system level functionality, or it could also mean improving the performance of an element. Automotive safety integrity levels, or ASILs, are not used in ISO 21448, although severity and controllability are used in the risk evaluation when hazardous behavior is identified. So they are only used to distinguish hazardous and non-hazardous scenarios. That means there is no hierarchy of methods in the standard. Sorry. Yes, so there's no hierarchy of methods within the standards, and the standard actually requires the developer to determine the criteria, what an acceptable level of risk is, and show that it has been achieved. Sorry, just having a drink to save my voice. As the functional insufficiencies are stimulated by triggering conditions, they're the main focus of the activities in ISO 21448, as I said. And with this slide, I just wanted to explain the philosophy that is behind the approach. Basically, the premise that is behind it all is that an ADAS feature or an automated driving functionality will either behave in a way that can be considered hazardous or non-hazardous in any particular scenario, and also that a scenario is either known to the designers or developers of the feature or unknown at any particular stage in the development process. And a hazardous scenario obviously is a scenario that contains a triggering condition that causes hazardous behavior. So in an ideal case, if all the scenarios that a feature is going to encounter when it's operating are known, then the developers should be able to design the intended functionality accordingly to only exhibit safe behavior. But of course, there is a huge, if not infinite number of scenarios out there in the world, and we also know that the technology that we have in place at the moment isn't perfect. But the intention of the methods described in ISO 21448 is to guide the engineer to identify sufficient hazardous scenarios so that they can be addressed with functional modifications or improvements, so that you can show that the performance meets the criteria set for the acceptable risk level. In the standard document, this is illustrated with the different types of scenarios that I've set out here. So known, unknown, hazardous, non-hazardous, represented as sets. And the intention of applying a SOTIF process is then to increase what is known as area 1 while reducing area 2, 3 and 4. So to summarize my presentation on the theory of SOTIF, so I'm showing now the outline of the process from the recently published full standard that was updated from the original pass. And you can hopefully see that the process is very iterative in nature. And this is this continuous improvement that I was talking about earlier. The top half of the process within the grey coloured box is intended to be performed through analysis and aims to guide engineers to a design that results in either no SOTIF risk remaining or a point where all identified remaining triggering conditions have been understood and accepted based on the criteria that are set as part of the process. And this is obviously a major difference to ISO 26262, where the risk classification and the implicit definition of what's acceptable is given within the standard. If the known triggering conditions have been understood, then the second half of the process in the blue box is where V&V activities take place that are intended to gather the required evidence that the scenarios have been sufficiently addressed and that the acceptance criteria have been achieved, as well as aiming to search and probe the scenario space as much as possible to reduce the uncertainty associated with the unknowns to the target level. There's also a new extension to the process you can see on the right to acknowledge that safety activities for these types of systems need to go beyond the design phase, and a new clause has been introduced setting out requirements for the operational phase activities of SOTIS, and you'll hear more about that later. And yeah, just to finish off then, so we've now got obviously this new process documented in ISO 21448 that's now been set out in 9 normative clauses. And although it's not as prescriptive as 26262, which is obviously a much larger publication, it's, I think, a much more improved description, and how it can be approached and used in practice is going to be presented next by Prashant. And so I say thank you and hand back over to John.
Thanks very much, Edith. I think that's given us a good understanding of the principles underpinning SOTIF and ISO 26262. I'd now like to hand over to Prashant Dajati, who's a senior safety engineer at Wave. He's more than 15 years of experience in function development, functional safety and SOTIF. And from 2018, he's led various SOTIF projects covering design, verification, and validation of driving automation systems from Sae Levels 0 to 4. As I said, he's currently a senior safety engineer at Wave, contributing to the development of a safety assurance framework for an end-to-end ML-based autonomous driving system. And today he's going to tell us about Wave's work implementing concepts from SOTIF and from other standards in their design work on self-driving vehicles. So Prashant, over to you.
Thank you, John. Hi, everyone. I'm Prashant. I work as Senior Safety Engineer at Wave. And we are a London-based startup trying to develop an end-to-end machine learning-based L4 autonomous driving system. So today, I'll be presenting our approach to the SOTIF concept phase. So let's talk about the agenda first. First, I will start by giving you an overview of the SOTIF concept phase so that you get a context of what I'm talking about in the consequent slides. Then I will explain how at Wave we do the activities of hazard analysis, hazard identification, risk evaluation, and the methods we use to identify functional insufficiencies and SOTIF triggering conditions. And finally, I will also briefly touch upon our method for requirements generation. And the key takeaway from the presentation is how Wave combines behavioral competencies analysis and STPA for the SOTIF concept phase. So let's crack on. So first, let's briefly talk about the SOTIF concept phase. So here you can see, first we start at clause 5, where we gather specification and design information to start our analysis. So here we gather information like the relevant operational design domain, the level of automation of the system, what kind of sensors we use, architecture, maps, etc. So this is the input for us to start with the activity of identification and evaluation of hazards. So here, similar to functional safety, we are just concerned with identifying what hazards can result with the system without trying to investigate what would cause it. And this is important because maybe there are hundreds of different triggering conditions that can cause an unintended forward collision warning. But if we consider it as not safety relevant, then we don't want to waste our time trying to investigate that. So once we do the risk analysis and we decide that some of the hazards are not acceptable safety-wise, then we go into the consequent steps of defining the specification for acceptance criteria. This could be something of the sorts, how many incidents we would allow for X number of kilometers, these kind of targets based on the risk. And then we start with the step of identifying and evaluating the potential functional insufficiencies. So functional insufficiencies are similar to malfunctions in 26262, but since there is nothing failing inside the system, the functional insufficiencies is either caused by insufficiency of specifications. This could be, as an example, maybe we forgot to consider some particular road signs. So that's why our system obviously will not react safely to them because it was not specified. Or it could be an issue of insufficiency of performance. That means even if we specified a particular behavior, the performance of our system is not good enough to actually meet that requirement. That could be maybe detecting pedestrians in the dark. Even though we intended to detect them, the light conditions show that the performance of our system is not good enough. So then we identify these triggering conditions and functional insufficiencies. Then we go to the phase where we have to evaluate the response of our system to these potential identified triggering conditions. And if we think the system already takes care of them and we have considered them in our design, we just send it over to the verification and validation phase so that they can be confirmed. But if not, we think our current behavior is not safe enough, then we go to the step of function modification. So this is where we maybe modify the function to improve the performance or reduce the ODD, etc. So when we do the function modification, it obviously has to be reflected now in the specifications and design documents, and the loop continues. So this is the overview of the SOTIF concept phase as per 21448. And today I will be going deeper into the aspects of how at WAVE we do the step of identification and evaluation of hazards, how we estimate the risks, and how we identify potential functional insufficiencies and triggering conditions. So now let's talk about hazard analysis. So here, once we have the inputs from the system and design specifications, we do something similar to functional safety, where we apply methods like HAZOP and we evaluate to identify vehicle level hazards. So this could be things like unintended braking or excessive steering, etc. So once we have this, we go into the critical step of identifying hazardous event. So this is where we deviate a little from functional safety, because in functional safety, what we are trying to do is identify the worst case scenarios, which gives us the highest SL. And since the origin of the malfunction is internal to the system, we are not really worried about all the possible operational scenarios. But for SOTIF, the unsafe behavior is triggered by an external condition outside the system. That means even though my hazard is loss of braking, the loss of braking at a stop sign, the cause for the loss of braking at a stop sign could be different from the cause of a loss of braking at an intersection. That's why we would like to have an elaborate list of all the possible hazardous events so that later we can analyze the root cause. So for this, what we do is we consider something called behavior competencies. So these are basically a skill set or the capabilities an autonomous system should have in a particular ODD. And we combine them with vehicle level hazards and that gives us an elaborate list of hazardous events. As an example, it could look something like this. So we have considered our functions of braking or steering. Applying the usual HAZOP, we get these vehicle level hazards like loss of deceleration, excessive steering, etc. And now when we combine these hazards with behavior competencies, we get very specific hazardous events. So this could be something like the vehicle does not decelerate to a stop sign, or vehicle does not steer at an intersection. So we want to have the hazardous events which is specific to our behavior competencies so that we can analyze them in more detail at the consequence step. So now that we have our hazardous events, now we go with the step of evaluating the risk of these hazardous events. So we follow a step something similar to what the standard recommends, is evaluating the severity and controllability of the hazardous event, and then having this classification of risk acceptable or not. But what we do at WAVE is we go one step further and classify the non-acceptable risk to different levels as well. So highest severity and controllability obviously gives us high risk, and maybe something that is not S0 but still has S1 and C1 gives us a low risk. And this is important for us because since our step for identifying the hazardous events is generates hundreds of situations that are interesting, we want to give some internal prioritization so that we can focus on the most critical issues first. So as an example, if there is a hazardous event of not decelerating to a stop sign, and the other one is decelerating insufficiently while yielding for another vehicle, when we apply the usual severity and controllability evaluation, we end up with high risk for the first event and a medium risk for the second event. And we do this so that we can give some priorities inside, and it helps us in better planning our next activities. But this doesn't mean that we don't take care of the medium risk or low risk events. It's just that we try to solve the high risk problem first before going to the medium and low risk hazardous events. And once we have done the hazardous events, and now we come to the critical step of identifying the functional insufficiencies and the triggering conditions. And for this, we combine STPA and SOTIF to give us this insight into the loss scenarios that can result in this unsafe behavior. So first, we take our hazardous events and we apply step 3 from STPA, which is identifying the unsafe control actions. So basically, we are looking at the control structure diagram, and we are trying to understand what kind of unsafe actions from different controllers can result in the same hazardous event. As an example, if we are thinking about loss of braking at a particular scenario, maybe it could result from the policy not providing the correct trajectory, or even if the policy provided the correct trajectory, maybe the trajectory controller did not execute the trajectory properly. In the end, both of these unsafe control actions would result in the same hazardous event. So what this step basically does is just investigates the architecture to understand what kind of control actions could create this hazardous behavior. Once we have that, we go to the step 4 and of STPA to identify the loss scenarios. And what we do here is we ask those various questions that the STPA handbook recommends, and we iterate it against various parameters of interest from the ODD. In the later stage, I will go into more detail of how this step is applied. But what we end up with is we have a list of potential insufficiency of specifications, the performance insufficiencies, and the triggering conditions from it. And what we do here is we deviate a little from the standard at the end here, because what the standard recommends is once you have this list, you compare it, you evaluate if your system's behavior is acceptable, and then decide if you want to do a function modification or not. But what we do at WAVE is when we identify a particular unsafe functional insufficiency or potential triggering conditions, we first define a performance requirement from him, so that even if there are some later changes in the design, the performance requirements are used as a reference. And then from the performance requirements, we see if our system meets these requirements and try and decide if we need function modification or not. And I will show you how that works in the later slides. So let's look at some examples of unsafe control actions from the step number 3. So this could look something like: the driving policy does not request braking while approaching a stop sign, or the trajectory controller accelerates towards traffic when stopped at a stop sign. So as you can see here, instead of talking at a vehicle level function, now we are talking about specific controllers that can result in this unsafe behavior. And what we are doing with this is we are capturing the relevant behavior competency we want to analyze, the hazardous event, and also the controller in question, because we also want to understand why would a particular controller behave in an unsafe way. Once we have the unsafe control actions, now comes the critical step of identifying the loss scenarios. So what we do here is we ask two main questions as recommended by the STPA method. So first is, why would the controller not understand the context correctly? So there are only two reasons why we would react unsafely to a particular operational scenario. Let's take the example of the stop sign again. So one would be if the controller does not detect the context correctly, and the second would be even if it detects it, for some reason it wouldn't react to it correctly. So what we do is we ask these questions as recommended by STPA one by one, and explore the various elements of our operational design domain to see if there is any factor in the ODD that can cause this unsafe behavior. For example, if we consider the controller receiving incorrect or corrupt feedback, and if we ask ourselves, is there any factor from the ODD which can result in this corrupted feedback so that the controller doesn't detect the context? So if we are talking about the stop sign, we can right away maybe look at things like low light condition or glare and say, yeah, so if there is glare facing my camera, then it will obviously not detect the road sign. That means my system will not understand the context. Even similarly, so here what we have identified is a potential performance insufficiency. So even if it was specified that we want to detect the stop sign, because of the glare, we are unable to detect that. Another example could be low light conditions. So maybe the stop sign is placed in a low light condition, and due to insufficiency of specifications, we did not specify that the headlights should be turned on autonomously. So that means without our lights, it will not be reflected on the stop sign and we will not see it. So in this case, what we have identified is insufficiency of specifications. So it was an issue of specifications. We never thought of this loss scenario, so we never specified for the system to autonomously turn on the headlights. So this kind of exploratory exercise will give, going through the ODD parameters would give you different loss scenarios. For example, if you again look at this, the second question of maybe we provide the correct feedback, but the controller interprets it incorrectly or ignores it. And if you think about why would that happen, one loss scenario we could think of is maybe it's getting conflicting information. Maybe the camera says there is a stop sign, and maybe our maps say there are no stop sign. So maybe the controller decided to give priority to the maps and ignored the correct feedback. So this is again insufficiency of specifications. Similarly, if you ask the third question of why would the controller receive the correct feedback or information after a delay, if we are not considering any functional safety issues, then exploring the ODD, you can think of various triggering conditions. For example, maybe there is a large vehicle in front of us and it is blocking most of our view. That means we will not see the stop sign until the last moment. And this is in a way receiving the information after a delay. Or maybe the stop sign is on a curved road, and when we the stop sign doesn't come into our field of view until the last moment. So what we are basically trying to do is systematically ask ourselves the various questions of what can cause this loss scenario and compare it with various elements which are relevant to our ODD to see if any of these factors can cause this kind of unsafe behavior. So once we have these loss scenarios, it is easier for us to start identifying the functional insufficiencies and triggering conditions, etc. So let's look at an example for that. Yeah. So if you look at this unsafe control action here, what it says is the driving policy does not request braking while approaching a stop sign. So from applying STPA, I could think of a causal factor saying the controller receives the incorrect feedback or the feedback is corrupted. And if you look at the ODD, one of the obvious examples that stands out is snow. So that means the stop sign was partially covered in snow, so my system couldn't detect. So it was unaware that it was approaching a stop sign, and then it ignored the stop sign and we enter into a traffic which has reduced visibility. So here, just exploring this causal factor question against various ODD parameters, we were able to identify a loss scenario. And from that, we can talk about what the functional insufficiency is. And in this case, it is a performance insufficiency, and that is the system cannot detect road signs covered in snow. And the potential triggering condition is quite obvious. It's the stop sign covered in snow. So once we have identified a potential triggering condition, only then we start discussing about the exposure rating. And it's always done based on frequency, because we can consider this as a pre-existing condition which is exposed when we come across a particular operational situation. So once we have this, we can think of writing a performance requirement. So finally, we have all the elements that we want. And what we do at Wave is, instead of directly going at evaluating the system's response to this triggering condition, we first write an implementation independent performance requirement. So in this case, as an example, we have written, the autonomous system shall be able to detect and react correctly to road signs covered in snow. So here, I'm not giving any cue about the solution. You can either improve your perception system to solve this problem, or you can depend on maps. So we don't care about it at this moment. So first, we write an implementation independent specification so that our design engineers and the test engineers and all can depend on this as a reference while they think about solutions or ways to test this system. So finally, to conclude, what we do here is we use behavior competencies and vehicle level hazards so that we can systematically identify elaborate list of hazardous events. And when we identify the hazardous events, we evaluate the risk and we give it different levels so that it helps us in better planning and prioritization. And finally, to identify the functional insufficiencies and triggering conditions, we use STPA method, and with the help from the ODD, we are able to systematically identify the functional insufficiencies. And the last point, first we generate implementation independent performance requirement, and later we think about how to modify the function to meet this requirement safely. And that's all. Thank you, John.
So Prashant, thank you very much. There's actually one question in the chat we may come to in the discussion session later. But so next, I'd like to introduce Siddhartha Kaskir. I think Siddhartha is well known to many of you as head of verification and validation of CAV at Warwick Manufacturing Group. He's run a number of projects for WMP, including use of simulation for testing amongst many others. He's been widely involved in development of standards, including a forthcoming standard on test scenarios for automated driving using ODD taxonomy. Has many awards, perhaps the most notable being a Forbes Under 30 Europe list in 2018, and also a winner of the UKRI Future Leaders Fellowship. Today is going to be talking about some important concepts in the V&V of automated vehicles, some of the work on standards, including a common scenario description language. So without further ado, Siddhartha, over to you.
Thanks a lot, John. Thanks for the very kind introduction. I'm going to talk today about the latest BSI standard in the area of automated driving system called BSI Flex 1889, and how that can enable us from to create an ODD or operationalize an ODD-based safety assurance framework. So what I would like to start off by saying is, if you take a step back and we're trying to prove that these automated driving systems are safe, there are essentially only three things that we need to work on from a research and a standards and a regulation perspective. So if you're trying to operationalize a scenario-based testing approach, which is what I think most of us now more or less agree to, you need a set of scenarios to start with. You need an environment to execute those scenarios in. And finally, you need to make a safety argument based on the evidence that you have generated. Irrespective of how complex or simple your system is, you will only need these three things. And the environment could be digital world environment, as in PC-based simulation. It could be a driving simulator. It could be a test track, or it could be real world. It doesn't matter. What I'm trying to say here is you only need three things in terms of scenarios, environment, test environment, and a way to make a safety argument. When you take it to the next level down, when it comes to an engineering approach to trying to operationalize this concept of scenarios, environment, and safety argument, you need to somehow create the scenarios, the content of the scenarios. You'll need to format that in a particular language, and then you'll need to store that in a particular database so that you don't reinvent the wheel all the time. So that's the scenario piece. Once you've got hundreds, if not thousands of scenarios, you'll need to plan where a particular scenario gets executed, either in simulation or in test track or in real world. And finally, you'll need to analyze each execution, if that was a pass or a fail, and then make a decision based on a number of scenarios, based on your coverage metrics and so on, to understand if your system is safe or not. So irrespective of your complexity of automated driving system, you will always follow the same flow of create, format, store, plan, execute, analyze, and decide. It doesn't change. It will always remain the same. Now, what we want to highlight here is that in order to operationalize this framework, and in order to do it in a scalable manner, we need to underpin this flow of create, format, store, plan, execute, analyze, and decide to an ODD and a behavior competency-based approach. Prashant did a fantastic job of trying to illustrate how ODD and behavior competencies can be used as part of an STPA process. But what I'm trying to suggest here is take a step back further, because what we are saying here is, in order to create a scalable approach, you need the entire flow to be underpinned by ODD and behavior competencies. And that will enable you to reuse your processes, your tools, in order to create multiple different automated driving systems with different ODDs. And in order to do that, you need a set of standards and tools so that you can ensure interoperability and scalability across the flow. So you need standards across create, format, store, plan, execute, analyze, and decide. So for some of you who are developing automated driving systems, some of you on the call who are researchers, some of you who are regulators, it's very important to appreciate that this flow of ODD-based scalable safety assurance framework has to be done in a manner that it meets the entire ecosystem of stakeholders. So in the cab space, in the automated driving industry space, you have the developers who are actually developing. So like Wave, who Prashant was representing, is a developer. You'll have tier 1 suppliers, you'll have governments and regulators, and you'll have researchers. And all these stakeholders will have very different requirements of each step of that flow. So even if we are saying we have an ODD-based safety assurance framework, that is not enough, because that needs to be tailored or customized to the requirements of that stakeholder. And the standards and the tools will need to be customized to the requirements of that stakeholder. And it's a very important concept that you need to understand today, because what I'm going to do today is illustrate how BSI Flex 1889 is trying to enable this ODD-based safety assurance framework, but do that from a government and a regulatory or a type approval perspective. Somebody who's trying to approve this system, somebody who's not a coder, not a programmer, how would they use a BSI Flex 1889 specification to actually enable the ODD-based safety assurance framework? So that's the focus of this area. So while other stakeholders like cab developers and researchers can also use it, our key focus for this presentation is the government and the regulatory and the type approval regime side of things. So for those of you who are very new to the concept of ODD, I just want to give you a very brief snippet around why I'm trying to say that everything needs to be underpinned by ODD. It's not the golden bullet. ODD is not by no means the golden bullet, but what I'm trying to say here is the flow that we have created needs to be underpinned by it so that the thing becomes scalable. And why I say that, you might have automated driving system deployments in Phoenix, Arizona, or you might have that in central London. The scenarios that you use in Phoenix, Arizona will be very different to the scenarios your automated driving system might experience in central London. So you can use scenario-based testing, but then you need to tailor those scenarios as a function of where you're going to deploy it, essentially as a function of your operating conditions. So that's why the type of scenarios that you use is very important. And the type of scenarios needs to be a function of your automated driving system's operational design domain. So ODD stands for operational design domain. So for those of you who are very, very new to the concept of ODD, I put in front of you the definition of ODD. I don't want you to read the entire definition, just focus on the first two words. ODD defines the operating conditions. So essentially it's trying to say, where is your automated driving system allowed to operate in? And it's a term that was introduced by SAE J3016 back in 2014, updated in 16, 18, and then most recently in 2021. So at a very top level, back in 2020, BSI had another standard, a pass called 1883, which provided a taxonomy for automated driving systems. At a very top level, it defines ODD at a scenery, environment, and dynamic elements level. Scenery, everything that is fixed. That environment, that is the weather and the connectivity side of things, and dynamic elements, things that move. So I'll highly recommend, for those of you who are not familiar with PAS 1883, go and have a read through it. It's freely available, and it's something that the whole assurance framework is underpinned by. So what is the role of Flex 1889 in this flow? So we've already highlighted that the flow needs to be a function of ODD and behavior competencies, but at the operational level, at a tangible level, what you're trying to create is the scenarios that you're going to execute in the different test environments. So what I'm going to do here is, because the focus is on Flex 1889, I'm going to only focus the discussion around the scenarios piece. I'm only going to talk about the create, the format, and the store piece. If people are interested in the plan, execute, analyze, design, happy to discuss that as part of Q&A or offline. So if you focus on the create, format, and store piece, the first thing you need to do in order to create scenarios is to understand what are the different methods of scenario creation. At WMG, we've created 8 different methods of scenario generation, which at a very top level follow 2 philosophies. One is a database scenario generation. The other one is a knowledge-based scenario generation. A database scenario generation essentially looks at real-world data, like insurance records, accident databases, real-world trial logs, to understand what kind of factors actually lead to near misses or accidents. However, you need to augment that by a knowledge-based scenario generation, because there's a big assumption in database scenario generation that automated driving systems will fail in a similar manner as as human drivers, which is possible, but not something that we have evidence for. So we need to augment the database scenario generation with a knowledge-based scenario generation. Prashant did a fantastic job of talking about STPA and how that could be used for scenario generation. If you want to go a level down, there's some publications out there. You can have a look through it. But what I'm trying to highlight here is the philosophy of knowledge-based and database scenario generation. It's not just that has remained to the world of standards. It's now also gone into regulations. So if you look into the EU regulation that was adopted for automated driving systems on 5th of August, you'll see a direct reference in the annex of that as knowledge-based and database scenario generation. Now, the fact that regulators have now started to refer to scenario-based testing and knowledge-based and scenario-based generation, we need to start understanding what kind of standards we need in order to enable this operationalization of this philosophy. And that's where BSI Flex 1889 comes in. So when you talk about formats, we're talking about formats from a regulatory, from a type approval, from people who are non-coders perspective. And so that's just to highlight, that's the stakeholder that we're trying to focus on in this presentation. There's a different set of standards, different suite of standards for other type of stakeholders, which we can discuss later on if there's time. So Flex 1889, the whole concept of Flex 1889 was that there was a need for natural language description or natural language format for abstract or functional scenarios. So while the title says abstract scenarios, it's something that can be used for functional scenarios, absolutely. The end users of the document or end users of the standard, if I may say so, are actually regulators, system engineers, but at a very top level, they are non-programmers, people who are not used to programming in C++ or Python or working with XML constructs, because most of the scenario definition languages or formats that you might have heard of that are already prevalent in the industry are essentially things that you go and execute on a simulation platform. So they are either XMLs, they're either Pythons or C++ files. That's not something a regulator would be willing to write in. So you want something that is more human intuitive, that's more accessible to a regulator. So that was a need that we're trying to address. It's very important, and I'd like to highlight this again. Please do not focus on creating standards for the sake of creating standards. Identify a gap, and we identified a gap here where there's a need for a format that regulators or system engineers and non-programmers could use. So the first version of the document was published in July of 2020. It's important to highlight that we published it as a Flex and not as a pass or a BSI standard, because we believe that a concept like this will go through iterations. It will go through lots of feedback rounds that will be out there. But it's also important to get something out in the industry for people to comment on. And that's why we took an approach of a Flex process, which in my experience in the whole standards world is the fastest way of actually updating standard content as compared to other standardization bodies like ISO or SAE or even ASAM. So the idea here is that we have made this public, and the consultation closed just on 30th of September, and we received lots of comments, which we're going to review and publish a next version very soon. So for those of you who haven't seen it, it's freely available on the BSI website. I put a link to the document, and we can also put a link to the chat for people on the call. So the important bit over here is at BSI, we're not wanting to create something that is just UK. We had an advisory group for this Flex 1889 that comprised of both UK experts as well as international experts. It had OEMs, tier ones, regulators, lawyers, insurers. And it's very important to highlight here that even people from OEMs and tier ones are not the people who are actually doing the simulation-based testing. They're people on the system side of things, where they're actually trying to define things in a more human-readable language. We've also provided tool support for the language, so you can also parse the language from an automation perspective. I mentioned public consultation closed September last month, actually. And we're planning a version 2 of the document after reviewing all the comments in Q1 of next year, which might be a bit here or maybe Q2, but we're looking at a target date is Q1 next year. So just to give you a very top level structure of what a scenario would look like in Flex 1889. So at the very top, you'll have a header for the scenario definition, and then you'll have the ODD constructs of scenery, dynamic elements, and environment. And so I purposely wanted to highlight this is because of the link it provides to the ODD-based safety assurance framework. Because you're providing your scenario definition also in terms of the ODD higher level attributes, it allows you to link scenarios to your ODD definition. So what are the key features of this language, and if you use it and define a scenario, what would you gain? So you'll gain human readability. It has a structured grammar to it, so if you want tools and parsers, you can create them. It provides you an overview of the scenario. Like any good language, it has the capability of extending it further. You are able to define both quantitative as well as qualitative parameters for scenario attributes. It's aligned with the ODD taxonomy, which is key, and which is key to enabling the ODD-based safety assurance framework. And for people who want to use it for even logical and concrete scenarios, you can. But the main purpose of this language is for abstract and functional scenarios. So to give you a very quick and a very succinct overview of the document itself. So we've got around 7 clauses in the document. From a standard set of clauses, we start off with the terms and definitions. But a very important concept I wanted to highlight here was the understanding of scenarios and how that differs from ODD and the role it has in scenario-based testing. So clause 4 is very important for us in the document. Then clause 7 actually goes into the language concepts in terms of the syntaxes that you might want to use. I don't want you to read the slide in front of you. What I'm trying to highlight here, it can get really complex if you look at each and every element of the syntax. So if you really want to use Flex 1889, and I highly recommend you doing that, read through the document in entirety. Don't just focus on the tables, because not everything in the table is actually of relevance maybe for your particular use case. So what this does is provides you the syntax of the scenario definition. And once you've formatted all these scenarios in Flex 1889, after you've created them using data and knowledge-based scenario generation methods, then you want to store them in a particular database. And you want to store it in a database such that it enables you to operationalize the ODD-based safety assurance framework. So for that, what we've done is we've created Safety Pool Scenario Database, which is the world's largest public scenario database, and it's roughly around 250,000 scenarios. But the key aspect over here is, and the reason I wanted to share this with you, is everything in Safety Pool, like in the Flex 1889 and the scenario generation, is underpinned by ODD and behavior competency definition. And that is important because if you're trying to operationalize this from a regulator's perspective, what would happen is if I am a regulator and somebody comes to me as a developer and says, please, could you approve this system? What I would do is I would ask them for the ODD attributes and the corresponding behavior competencies of their system. Then I would use that as a way to search the Safety Pool Scenario Database to get all the relevant scenarios. Because I can do that, because Flex 1889 also is underpinned by the ODD and behavior competency attributes. And then you can make a case for completeness by comparing it with metrics which are also ODD based. I haven't gone into the details of this, the way you create the metrics, but that's a separate conversation. But what I wanted to highlight here was the journey from left to right is possible only because you have the standards like Flex 1889 and PAS 1883, but also you have tools that enable the operationalization of those standards. Before I end, one of the things that I wanted to highlight here is Flex 1889 is just one standard or one future standard in a myriad of standards that we need in this area. We need standards and tools across each stage of the safety assurance framework, across create, format, store, plan, execute, analyze, and decide. There are existing standards for each of them, and there are gaps in some areas. Flex 1889 identified a gap, and it filled that gap. That does not mean it has filled everything. So again, I would like to highlight, it's not the golden bullet, it is just one cog in the wheel of safety assurance. So in summary, what I'd like to say is every aspect of the safety assurance framework or the testing framework for automated driving system has to consider its relationship with ODD. The scenarios need to be a function of ODD, the metrics are a function of ODD, the simulation fidelity requirements is a function of ODD, but it's not enough to just talk in the philosophical manner. You need to have concrete tools and methods to convert this into concrete implementation. And it's important that we do not forget the types of stakeholders we have. We have the regulators as well as we have the developers. So it's important to have focus on that. And my appeal to the ecosystem, especially the people who are on the call, and given this is a BSI webinar, is let's address gaps in standards. Let's not create competing standards just for the sake of another document out there. There are enough gaps out there in this ecosystem that need to be filled. And lastly, I would like to just say thank you to BSI, thank you, John, and looking forward to the Q&A session.
Thanks very much, Siddhartha. So I think without further ado, we'll sort of move on. So the next talk is from Paul Spence. Paul was Chief Technologist at McLaren for over 25 years. He led on telemetry and analysis tools that are a key part of Formula One's rapid development and decision cycles, and he developed many of the key tools that help the teams get the best out of their data, as well as helping the FAA regulate more objectively through the sharing and standardization of the data. Paul is now working for PKS Insights on automated vehicles, particularly as part of a BSI feasibility study, looking at how data can enable operational monitoring of automated vehicles, including things such as digital commentary driving. I'll hand over to Paul now to talk about some of the more operational phases of use of autonomous systems.
Hello everyone, and thank you for that introduction, and John. So what I want to really just talk about is the digital commentary driving, but just to sort of set the scene a little bit and really focus on what DCD is really intended to achieve, and it's really about measurement. So I'll give a little bit of background. So systematic verification and validation with a sort of an oversight, which is where so DCD may think. Then really what DCD is about, and then some further work that we're looking at. So, but now the progress to fully autonomous vehicles has, it started perhaps with some fairly futuristic thoughts in '74. You've seen some pictures. About 5 years ago, everyone got very excited. It all seemed quite possible, and now there's a little bit of a realization of just quite how hard it is. It's they realize when you develop these side of things, you sort out a few big hurdles pretty quickly, and then you find more and more edge cases that are really difficult to achieve and to deal with. And the reality of driving in the real world is that there are obviously too many accidents, but they are actually very far and few between. Most of us drive many miles and survive them, and those it's very small percentages. And so we're really trying to achieve something very tough with automated driving. The cost of failure is very high, clearly, if you do have accidents, and it's a dangerous thing that we do. But we've got to find a way, because the alternatives, ADAS devices can fix a lot of the accidents that happen now, but they're really based on fixing human failures. And when we get distracted, or when we don't pay proper attention, the rest of it, they themselves will find it, without the full context that you have in a full automated vehicle, it's very difficult to be fully safe. And there is some evidence that actually accident rates are going up now, not down. I mean, despite numbers of journeys and things actually having gone down over the past few years, people are getting a little bit more easily distracted and relying on ADAS too much. So we have to find a way to get to that goal of when we actually do have really good quality, fully autonomous vehicles that can drive in a society where we are still free to wander around, and there are still non-autonomous vehicles, or people walking, children playing, animals straying from where they should be, all the sort of stuff that happens in a mixed society. So we have to find a way. And for all my background, the fastest way to make progress is that if you have a good measurement system, you really need to be able to measure. If you can't measure, everything is trial and error, and it's guesswork, and it just takes for absolutely forever. So so really what I'm trying to focus on is on measurement. So there's clearly a lot of work that needs to be done on the systematic approach, and we've heard lots about SOTIF and 26262, and that's really detailed. You have to go through all the processes. You really have to understand every little thing, but it's quite hard to stand back and say, have you really thought of everything? How do you know that all these things are going on? And the only way you can do that in a way is if you can compare different vehicles and different people, and how people have come to things. So if something's developed in America and something's developed in the UK and something else is developed in Japan, they will have differences. And if you can compare them, you will find out some interesting things, and you may well be able to nudge and push and the rest of it to get an overall better solution. So we do have to find ways that we can measure while still protecting all the IP and the know-how that these individual people have. So it's not about just sort of spreading the technology of one company to everyone, but it's really important that we have some oversight in how this this can work. So BSI sort of it must have been a year ago or so asked a group of us, Nick Reed and Siddhartha, to look into what would be a set of KPIs that would actually say, well, one AV stack is as good as another. And we struggled actually to find any sensible benchmarks that you would actually say how to judge, because the environment of driving is so complex, and because there's very few truths that are really out there. So we really came across thought about this and talked to lots of people. And there's a report there, but what we realized is the only truth, or it's very difficult to find truths in the real world, because you don't know when something has a particular action whether that was the best thing or not, because you don't know what was around it or the rest of it. And you can do some tough testing at test tracks, but in the real world it's very complex, and so we don't know. So we did that, and then we also did another little bit of project where we actually instrumented up a simulation system. So what is digital commentary? Well, it comes from the concept that as an advanced driving test, one of the things that the examiner will do is ask the candidate to give a running commentary of what they can see, what they think will happen, and just what are the risks that are going on. And that way you can assess whether that candidate is aware of all the things that are going on, and it's a very good way of understanding that person. Now, clearly, in that situation, you've got one human judging another, and that's a closed system, and that works. But and there's a limitation as to how much a person could say. They can obviously prioritize certain things. But in an AV stack, in a computational way, then we can make some of that information much faster. Now, what we're trying to do is give an explanation at a really high level of what can be perceived and what can be seen, and predicting what's going to happen in the next few seconds. So it is outcome based. It's not about how you got to that conclusion. It's not about understanding the raw data. You cannot make a super AV that measures a candidate AV. So it is about using high level data that, as I say, is independent of the raw data and independent of the sort of IP and the implementation. And then you can use that data to come up with new KPIs that actually give you the real things that you need to understand as to what is safe and what is not safe, and for that to evolve, because as we make progress, we'll find more and more cases of how we judge whether something is safe or not. It's important that any measurement system is both valid in simulation and real world. And as John mentioned, I spent 20 years in F1, and if there's anything you learn in F1 is that you have to evolve through simulation. But simulation, if it's on its own, gives you some false confidence. It sounds like you seem to get some very precise numbers. Those precise numbers have to be correlated with the real world all the time, and it's that correlation with the real world that gives you your progress, encapsulates your knowledge that you're building up, and so it's really important that any tools work both in simulation and the real world. And lastly, there's always a fear that this is going to be huge volumes of data and the rest of it. It won't be. It can be very small, simplistic, and lightweight. So what might that mean? So The AV stack can be considered a black box. It has to decide what it's going to do. It's going to drive. To be safe, you have to know where you are going to be able to go and what the other people are going to do. And the space that you are going to be able to drive in has to be free. Well, you have to believe it's free. And your ability to believe that space is free is a very big part of whether you're driving safely or not. So perhaps three components. One is you've got to be able to perceive what's around you. And a reality is that it's quite hard to see things from a distance, but as you get closer, then you are more likely to be able to see them. So if you have recorded what the AV thinks it can see at 100 meters, and you compare that with what it sees at 5 meters, you're likely to get a better picture of what that of whether it was right at 100 meters or not. If you monitor what it predicts those objects are going to do, you can of course use hindsight essentially to see whether that prediction was right. Now, it doesn't have to be perfect, of course, as long as people stand on the pavement and it doesn't matter where they walk, but if they look like they might step off, then you want to know that that's a possibility, and you've sort of accounted for it. And thirdly, there is the point about control. Do you drive where you say you're going to drive? And again, that doesn't have to be precisely right, but it should be that you are able to do what you say you're going to do. And this is not about sort of instant failure if you get any of this wrong. This is about producing a data set that you can provide reasoned judgments from, and that it is has a much higher fidelity than any other type of mention of number of disengagements or number of miles driven or any of those things. Those are or even accidents. Those are very, very coarse measurements. What we're looking for here is that you can measure things much more precisely and get early warnings of issues rather than actually waiting for something to go wrong. You will never fix the last fault with trial and error, and clearly there's a big if you take what happened with Boeing, the 737 MAX, if you take what happened with Dieselgate, those are issues where the trust in big organizations has been violated, and you need the regulators and need visibility. With the Boeing, in a way, the processes were so complicated that people got lost in the weeds of those processes. So you need this complementary visibility and measurement tools that you can say, actually, this I understand this makes sense, and this seems to be going according to plan, and I can see everyone I can compare different OEMs in the real world, and I can understand how it operates. And just a bit more about what it might actually mean. So there's the UN ECE has stated that there must be in-service monitoring as one of the pillars to making autonomous vehicles safety, alongside the simulation and the track testing and all the auditing that covers whether you followed SOTIF and whatever standards. But there has to be some sort of in-service monitoring that actually gives us feedback about what's going on, and so this is, in a way, is directed at that. So what it might mean is that there's a listener in the vehicle, and it basically just monitors what's going on, and if there's something abnormal, which obviously is not expected to be very common, but if there is something abnormal, then it can raise an event, collect a bit of data, all from this sort of prediction stuff, and then that can be looked at in more detail in a cloud environment. Now, it's very likely that you would get false positives on the vehicle because it doesn't have the full context, and then those false positives could be ironed out in a cloud environment. But it could be lightweight enough that you would actually not need to send out very much data at all. So now, what is the sort of target market of DCD? Well, it's really the consumers of one form or another. So regulators need the ability to understand what the vehicle is doing now, and those regulators have to have one of the things that people don't fully grasp is how good they are at understanding images. And we often use the phrase that a picture's worth 1,000 words, where for an AV or a computer of any type, 1,000 words is much more useful than a picture. And 5 megabytes of an image is really useful to a human being, but 5 megabytes of what's in that picture in a structured way is what the AV stack has to do, and it is very difficult to do that process. And so when we see a picture, we assume that the computer has understood everything in that picture, and it is far from the truth. And so when we're, as the sort of bystanders to this development, when we are trying to understand what's going on, we're very at a high risk of making poor judgments. And so we really need to make this data accessible. And large volume of people drive with this experience we do. A lot of it comes down to us understanding body language and the rest of it. And we have to find ways of making this data accessible to those people, and then also providing tools that they can then judge and compare on that data. And it's important that you effectively separate out some of this testing with how the stack has been implemented, so the same tests can be applied to multiple vehicles or multiple AV stacks and move the bar forward that way. So and there will need to be the ability for, there'll be a lot of people that will use AV in one form or another, whether they're service providers, whether they're cities, whether they're regulators, insurance companies. They need ways to be able to define SLAs and say, I want the vehicle to be a little bit safer in this environment. I'm getting a few warnings that it's not quite as good as it should be in such and such a situation. And that, if we can create those tools, people will be able to resolve the issues much more quickly. They'll be able to fix things without necessarily breaking something else, and you'll make the progress that we need to do. I'm just getting on time, but one of the important things is it's got to be trustworthy data, so it can't be that the vehicle records all this data and basically processes its outcome, and of course it's subject to whether that's what you saw, and if it's 100 milliseconds when the vehicle wasn't sure about what it was doing, it's not safe just to assume that in 100 milliseconds everything will be clear again. It looks like that when you see it on a graph. 100 milliseconds looks like a brief dropout, but maybe 100 milliseconds is the time you've got to start reacting, and so you do have to be able to see this data live. As long as it's sent live, then it will be trustworthy, because the data cannot be, if the AV can predict the future through black magic, then great, but if it can consistently predict the future, then it is doing a fantastic job. And that's really the key, that there is no easy way around about predicting the future. It has to be done through transparency and honesty, and so that's one of the sort of key tools that I think we can use to make sure that these vehicles are safe and avoid any other sort of Dieselgate or Boeing type problems. Yeah. So no, there's a lot of work to still do, but it needs the some more engagement with the OEMs, because they are understandably protective. They understand they are very focused on the work they're doing. They don't want to be disturbed, and you've got to respect that. The regulators are starting to understand how difficult the problem is, and there's understanding of responsibilities. So we really need to do this. We've done a little bit of work on trying to
Yeah, Paul, thank you. And I think this notion of digital commentary driving is very interesting. Maybe we'll come back to that in the discussion. So I'd now like to turn to our last speaker, Brian Wong, who's a partner at Burgess Salmon LLP. Brian chairs the firm's transport technology and intelligent transport practice, which includes involvement in 5 Innovate connected autonomous vehicle projects. They've also been involved in supporting Zenzik on work on cybersecurity and operation of off-highway automated vehicles, and that's involved looking at aspects of liability, safety, cybersecurity, regulation, and insurance. So a very broad, non-technical perspective. So Brian's going to tell us about the state of the law and regulation in the UK, how we manage some of the key issues around public trust, given concerns about responsibility, accountability, and liability. And if that wasn't enough, explain what's going to happen in terms of the upcoming legislation that's going to occur in the UK in only 15 minutes. So Brian, over to you.
Thank you, John. That's a good challenge for me. Yes, as he says, I've only got about 15 minutes to explain why, I guess, over 100 years worth of UK law is going to change and why it needs to change. So from this introduction slide, I think I'm just going to crack on. So when lawyers talk about a regulatory framework, we're very much looking at it in terms of a pyramid with UK legislation and case law at the top. That's law as made by Parliament and government, as interpreted by courts and judges. And fundamentally, that establishes what is and was not legally required or permissible here. So sometimes that is informed by international obligations on the UK as implemented into domestic law. And this body of legislation in turn might mandate compliance with certain specific technical standards or empower regulators or agencies to adopt them and require compliance. And this second layer has in effect the force of law, and failure to comply with that normally involves a breach of a legal requirement above. But below this second layer, and in particular in highly technical areas, as we've already talked about, you may have a very large body of voluntary standards and practices, filling in the gaps and expanding for the benefit of industry through expert working groups, how the law might apply, what is reasonable, what is good industry practice, what is best practice. Whilst compliance with these is not mandatory, very often they're considered, as I say, good or best practice, and occasionally you'll find that mandated requirements in the second layer above, they do sometimes require regulated entities to adopt unspecified kind of best industry practices. And then you really want to be looking in that layer below to see what those best industry practices might be. And inevitably, there is a relationship between these layers. So often you see voluntary standards and guidance which emerge, which become so accepted and so core over time that they become mandated by law and become part of the law ultimately. Ultimately, you might have legal standards above, which are so general and so generic that the kind of need for industry practice and standards like the BSI standards and the flex PASs and all the rest of it that we've been talking about are. So that's the regulatory pyramid, and it's going to be very familiar actually to those who are in the automotive industry, for example. So you've got a number of generic and specific UK laws at the top. You've got a set of mandatory technical, usually type approval regulations underpinned by an international treaty-based system below the law. And then you have a lot of continuous national and international standards development ongoing, much like the work the BSI has been doing. So where has the UK's regulatory focus been to date? Well, it's fair to say that much of it has been on getting cabs ready for the public road, as opposed to what you might call private space. Certainly you can see that in BSI's work, the CCAV codes of practice. And in the UK, the Law Commission's kind of 4-year project to look at reforming the road traffic rules for automated vehicles. It's also where the single UK piece of legislation dealing with automated vehicles, the Automated and Electric Vehicles Act 2018, currently sits as well. That's not to say that there aren't CAVs being used or considered for private spaces. That's really far from it. But as a matter of law, the use of vehicles purely in those private spaces is conventionally something more about the landowners or those who employ and control those workspaces, as opposed to being a public environment where Parliament and government needs to intervene. I've tried in this diagram just to indicate that there is a blurred line sometimes between what is a public road and a private space, and very often those who are trialing CAVs or considering deployments just need to be a bit careful with that distinction, because there is actually no clear distinction in law, and sometimes what you think is a public road isn't at all, and sometimes what you think is a private space isn't at all, and so you just need to be a bit careful. It really depends on how the general public use the relevant space you're talking about. Nevertheless, in that public road arena, the UK's regulatory focus to date has certainly been about getting the UK roads ready in these 3 key areas: kind of safety, liability, and insurance. So that's been the focus for the Law Commission's work to date, as well as much of the work of CCAV, as well as some of the preparatory changes that have been made to the highway code to date. And in respect of those regulatory focus points, I thought I might just illustrate a bit about why the key issues have been from a lawyer's point of view. And I expect most people on this call, they're going to be familiar with the SAE Levels of Automation, first published by the SAE in 2014, and really it's been perplexing lawyers ever since. And I just wanted to explain a little bit why it's been that difficult. I guess first of all, levels of driving automation, that's a really legally difficult concept. So far as the law is concerned, you either are automated or you aren't automated, and that especially applies when you look at levels 0, 1 to 2, which talk about increasing amounts of assistance, but from a legal point of view, it is basically just driving as it's always been, with an increasing amount of assistance, but a human driver is still the human driver. For levels 4 and 5, this is certainly automated driving when active. The human driver is not needed when engaged, as the vehicle is able to safely drive itself. And this is the core definition of what automated vehicle is under the Automated and Electric Vehicles Act. Level 5, of course, being that kind of drive itself anywhere, anytime. But level 4 being self-drive, but only under limited conditions or ODDs, and only when those conditions are met. Level 3 is much more complicated, and it's what the Law Commission's called the Mushy Middle. And from a lawyer's point of view, it's a bit of a minefield. So within level 3, you still have, like level 4, the ability of the vehicle to drive itself under certain limit conditions when conditions are met. But unlike level 4, when the feature requests, the human driver must drive. So the human in the loop is an essential part of the design of level 3. And this means that there is, frankly, a need for takeover. And this takeover has understandably raised a great number of questions for lawyers ever since CAVs have first started being trialed in 2014 and before, actually. But in general, the relationship between humans and machine in levels 3 and 4, where either may undertake part of the driving task, is conceptually actually quite novel to the law, and it challenges, as I say, over a centuries-old body of law that's only ever really seen driving as a human task and judged driving against human capabilities, limitations, and errors. So if you ask a lawyer, what does this look like when it translates into law? This is Broadly, what the law commission's work and the government's response to that says that it should probably come out as, by the time this is kind of legalized. So on the left-hand side, you've got ADAS, increasing amounts of assistance, but as I say, essentially status quo from the point of view of the law. There's going to be a clear, bright line distinction illustrated on this chart by a clear, bright line between that assistance and what is automated on the right. And within the automated driving system side of things, I don't really have the time to go into the full detail of the law, but essentially this is a full new legal system on the left-hand side, where if a vehicle requires a human in the loop, either for safety critical reasons or at some point because its ODD is so limited, then it would be considered a Category 1 ADS in orange. And if it doesn't require a human in the loop at all, then it is Category 2 ADS. But unlike SAE, whereby you've just got these kind of levels, this very much recognizes that you can have both. You can have vehicles which, when certain conditions apply, will need a driver, will need a human in the loop or a user in charge. Or in other circumstances, for example, if you've got valet parking as a function in your vehicle, it may not do, in which case you would have a Category 2 element to it as well. And so you might have to be authorized for both. The whole thing it pins on a new safety regime, which is going to be very novel for the automotive sector. You've got type approval, you've got pre-deployment safety assessment. That's fairly standard so far as automotive sector goes, but it's going to be rolled into a whole new system of in-use monitoring and surveillance. So once vehicles are authorized to operate on the road, they will be required to report certain data. They will be required to cooperate with regulators, and they will be required potentially cooperate with a new accident investigation body as well. And when I say we, in particular, it will be the authorized self-driving entity or the ASD, who the law is going to designate. If you put your vehicle forward for approval, then you will essentially have to answer to the authorities for it. Taking this emerging framework forward then, I just wanted to focus a little bit longer on this safety side of things, which is, as I say, incredibly novel for the automotive industry. The UK has set out its stall in terms of that it will create a new authorization framework in the UK for these vehicles specifically. It will be guided by an overall safety ambition. That safety ambition is being consulted on by the government currently, and that consultation closes on the 14th of October, so in 3 days' time. And the proposed safety ambition is that self-driving vehicles would be expected to achieve an equivalent level of safety to that of a competent and careful human driver. What that is not yet defined, but in terms of the kind of current tests that the government is proposing for authorizing the vehicles, the slide here has a list of some of the things that certainly will include, things like complying with traffic rules, avoiding collisions, avoiding putting yourself in a position where it could cause a collision, and so on, and recognizing when you're in your ODD or outside, some core aspects of what safe driving might look like. And recognizing that my time is over, if not coming up, I thought I'd just highlight the current areas of focus and priority, as well as all the emerging framework stuff that we've talked before. And it is supposed to come in legislation, but the legislation is currently delayed, so it is likely to be pulled out of what is a mammoth Transport Act and possibly put into a separate legislation of its own, but who knows? We're all waiting for parliamentary plans. But in terms of things that still need working on, very clearly, digital highway code and road rules have been discussed already, very much endorsed that needs to be the case, that it's core to understanding what an ADS needs to do to comply with and ultimately SIT, its driving test. This idea of a competent and careful driver is quite a complex one because, as I discussed beforehand, it's fundamentally a human test. And actually, legally speaking, it's previously been defined mostly in a kind of what it is not. So we are better at defining what an incompetent and a not careful driver is than the other way around. We've got the technical framework that's being worked on in the UK, but we are seeing signs of what that might look like, especially if it's going to integrate with the UNECE and EU type approval frameworks, which are emerging. And I think people have already mentioned data and cybersecurity as key concerns. I'd love to talk about that more at the Q&A, but for us as well, transition demands, that takeover remains a critical issue for Category 1 automated driving systems. How do you achieve a safe and reasonable handover between human and machine? And at that point, I was just going to hand back to John.
Brian, thank you. That was an extremely lucid summary of what's a very, very complex subject. So thank you very much from that. So I'd like to invite you and the other presenters to join me in the panel session here. I've had a number of questions beforehand and some submitted online. I wanted to start off with one technical one that I think in a way gets to some of the core issues. And if I could perhaps ask Prashant to start first, and maybe as others want to comment, which was, do you find that SOTIF identifies the same set of hazards as functional safety, or are there different hazards found for SOTIF? And I think I know what the answer ought to be, but I'd be interested to hear the truth from the real world.
Yeah, no, that's right. So the hazards are more or less the same because we are looking at vehicle level consequence of different things. So if we are talking about an autonomous system, we are basically maybe controlling the brakes, the propulsion, the steering, and maybe the lights. So in the end, the hazards are the same, but the source of the hazard is different. For functional safety, it is internal malfunctions. So it could be random hardware failures or software errors, etc. But for SOTIF, the source of the misbehavior comes from outside the system itself. It could be driver misuse or operational situations, etc. So the hazards are the same, but the causes are not.
Yeah, thank you. That's interesting. That's exactly what I would have said. I don't know if any of my fellow panelists would like to comment on that as well, or do we all agree that Prashant has summarized that extremely well?
I might just make a few remarks. I absolutely agree, but what I've found sometimes already, it's a question how you actually formulate it, though, because we're very much used to in the world of functional safety to talk about, for example, a hazard of undemanded acceleration. What we didn't actually specify at the time is that it's undemanded with respect to what the driver wanted. So the driver didn't want acceleration, but the system is giving acceleration. Now, of course, we're referencing it to the scenario. We're in a scenario that does not require acceleration, but the system creates acceleration. That's really, I think that's what you were trying to say as well. But it's just when you're actually documenting it, how you capture it is sometimes a key to actually tease out those differences.
Yeah, thanks, Edith. So unless there are all comments, let me turn to another question here. So does functional modification to resolve insufficiencies require further reevaluation, e.g. through HAZOP? And I see lots of nods. Siddhartha, did you want to lead on that, and then maybe to turn to colleagues?
I think it depends on what the change is that you're trying to create as a result to mitigate the insufficiency that you've identified. And I personally generally use STPA as a way of doing this. Once you've identified the insufficiency, you'll put in some mitigation, then the number of things that it impacts in the control structure, those are the aspects that I would reevaluate. You don't need to do the whole analysis again, but you need to be very sure about the things that it is impacting, and the control structure is the best way of identifying that.
Yeah, I think that's good. If colleagues have any further comments to that, that would be fine. But if not, I mean, this if you like leads on to what I think is a rather related question. Saying, you know, the process looks very human resource heavy. You know, how would you do the heavy manual work? How do you evaluate coverage? Now, I know the gentleman who posted this, who works for a company that does automated safety analysis in the rail industry. So, you know, he has some experience of automating these sorts of processes. So colleagues, what do you think about that? How heavyweight is it? Is this an employment scam for safety engineers, or who wants to lead? Prashant, perhaps?
Yeah, so finally, when I'm talking about SOTIF now, so when we are analyzing this, we have the two main categories. We are worried about the known unsafe scenarios and the unknown unsafe scenarios. So to get a higher coverage of the known unsafe scenarios, just brainstorming or these kind of discussions is not enough. Then you will have to be discovering lots and lots of unknown unsafe scenarios while testing, verification, validation. So the best way to do it is to have a systematic method, could be different to the one I explained today, but to be as rigorous as possible in the design phase so that we identify an elaborate list of these triggering conditions, and we are already prepared. And the whole idea is to shift the burden of discovering through testing to the analysis phase. And the coverage of this is obviously a function of the operational design domain. So if we are designing a simple function which just does some loops inside a university, it is much easier to think of all the possible operational design domain like parameters and kind of do an estimation of the coverage, right? But if we are talking about a function that runs all over the country, then it becomes much more complex. So there is no easy way to perfectly measure the coverage because we don't have like the end list and we are just trying to meet them. There is this aspect of the unknown unsafe scenarios. So there is a big unknown chunk. The whole idea is to be more systematic and rigorous through system engineering so that we at least try to find out as much as possible initially and not leave everything to testing.
Yeah, I think that makes a great deal of sense. Try to shift things into the analytical space rather than testing. I think is exactly right. But I think a lot of that analysis is going to be manual. I think you can do some things to check that and support it, but it is going to require quite a lot of activity, which actually in a way relates to one of the questions that was submitted before, which is, can the safety analysis methods based on expert experience adequately identify triggering conditions in complex ADAS systems? Is there any method that can help to find the edge case and corner cases? So I think in a way it flows on for that. Maybe you'd want to follow up, or maybe Edith or Siddhartha would like to comment a little as well.
Maybe I'll have a go at that. I think there is no golden method that I can say that there's one method and you do that and you will find all edge cases. That's not going to happen. That's not true. You'll have to take an hybrid approach, and some of the from our experience, we believe you need to be driven by both the expert side but also the data side. There is so much in real world data that you can get out of once you analyze it in the right manner, which is also a separate question. But you need to take a hybrid approach. Expert knowledge is a big part of it, but you need to take real world data also into account: accident databases, insurance claim records, trial data. And if you look at the EU regulation also, it also mentions something on those lines.
I would say that the regulatory changes that are coming, they do actually recognize that far more than what the current type approval framework and vehicle certification framework looks like. You know, what is coming in the future is very much recognizing that once these vehicles leave a into the marketplace, once they're out there, the continuous data loop and the safety learning must continue. And actually, you cannot just write a single safety case and then get it through approval and then put it into a drawer. It assumes that you will not find all the edge cases and corner cases. In fact, it assumes that more will be found and that you must address your system to deal with them as they arise.
Yeah, Brian, thank you. I think that's actually a very helpful observation. And to me, this is one of the really big differences about this sort of autonomous driving, that it's always been the case that we know you won't find everything. We now have to make that much more explicit and accept it much more, which I think actually leads on sort of quite well to one of the other questions, which is about how we manage maintenance and operation of autonomous vehicles. And I know, Paul, you mainly talked about the digital commentary driving, more as a way of sort of evaluating systems, but I think this is also relevant in operation and use as well, isn't it? So do you want to start us on this issue about how we manage maintenance and operation of autonomous vehicles? Another small question.
Yes, I mean, absolutely that the observation that you would pick up from DCD should, if it matters, pick up that some sensor or some part of the system is not working as properly. So that is the idea, is really to give you a good picture of what's going on, and a much richer. And I always argue about engineering processes. The efficiency is very, very important. It's very easy to do track testing and just waste weeks of time at a track and learn only a tiny bit. And obviously, motor racing is an extreme aspect of that. But when you've got hundreds of engineers trying to use a 1 hour slot to get to within a few percent of the laws of physics, it is a fantastic ecosystem to create engineering processes that are absolutely on the edge. And now we don't have that pressure in actually in the automotive world, and actually in telecoms as well. And so the trial and error has filled in some of that stuff, and a lot of time gets spent just doing stuff but not learning from stuff, and that is really what you're trying to do with a measurement tool, is actually improve that efficiency. So absolutely, one of those things is learning the impact of degrading sensors because they've been knocked, because they're covered with a bit of snow or a bit of tire and all those sort of stuff. It is really is understanding that and building up a good picture, because we won't get enough accidents that tell us that all the different sensors on the car. If you've done the degrees of freedom on a car, an age of sensors, an environment, it is a massive space, and you want 100 data. You want 10 data points for everything you want to make a decision about. We won't get 10 data points if we just look at that. But if we pick up near misses, maybe near misses are at least an order or two more dense in terms of information than actual accidents. That's the push. Anyway, engineering efficiency, that's a real world thing.
Yeah. I mean, that's a very helpful perspective, and I think there are going to be many broader issues as well. I mean, some of which will impinge on the legal perspective. If manufacturer A finds a problem with this analysis, how do under what circumstances that pass on to other manufacturers as well? But you're right. You need that sort of basic technical framework to be able to do that.
It's important that a regulator can understand what's evolving and react before it becomes a crisis. So, if a car maker in the US can be, if the regulator has the power and the knowledge to say you are below par, let's have a quiet conversation about it, get your act together and move forward, rather than suddenly getting to the point where actually there's a very big recall and or Boeing's out of the air for a couple of years, and it gets very, very expensive. And I mean, if there was a big crisis of confidence in AV, it could kill the whole thing, because you get to a point where someone says, until you proved it's safe, you're not getting back on the roads. If you get to that point, then no one can develop it, because they can't get on the roads to to move forward. So we've got to have, a way of managing the pressure, and that's what I'm doing.
Yeah, thanks, Paul. I quite agree with that. There are a couple of questions that are sort of posed more in a sort of regulatory space. Maybe this is Brian first, and maybe something a little bit more technical. But one is saying that if we have different sorts of vehicles, private vehicles, public transport, buses, freight, do we see any major differences in those? I think, you know, both technically, but also from a sort of a legal perspective.
Yeah. So I mean, currently they are different legally. You know, if I can drive a car, but I can't drive a bus. You know, I can't drive a lorry. So they are all commercial vehicles are separately regulated, as well as kind of, you know, basic kind of driving and construction and use reg compliance. And so even with the emerging framework, sorry, I didn't have a chance to go into this in that chart, but within there's the idea that if you are operating vehicles commercially, either for passenger transport or for freight and logistics, the proposed framework is that you need to license yourself as an operator, much the same way as you do today, and that much of the standard tests will apply as they do today, you know, whether or not you have good financial standing, whether or not you have a good safety record. And there's no doubt, I think, that it'll differentiate in much the same way as it does today as well. So if you're carrying particularly dangerous cargo, then there will be additional layers of regulation on top of that. None of that is going to change. And I think from a public perception of safety point of view and a public assurance point of view, that is probably the right conclusion for the UK.
Right. Yeah. Thank you. That's a very clear answer. Let's hope that's what ends up going through Parliament. There. There's another question relating to things that are sort of quite close to deployment, and maybe there's a legal perspective here, but also think very much a technical one. So how do the panelists think consumers are being informed of the limitations of autonomy, particularly at level 3 with things like the automatic lane keeping system, with the driver manufacturers sell more vehicles and systems with often misleading system names? What should the response of regulators and standard makers be to this? So I don't know. I mean, Edith, do you want to start on that? Then maybe we can come back to some more of the of some of your colleagues and also some of the legal perspective there.
Yes, a good question. I can probably only answer from a technical point of view, and I think the intention is, and as I talked briefly about it in my presentation, misuse. The concept of misuse has been extended in the full SOTIF standard directly because of this issue you just mentioned. But I also see it to some extent a little bit closer to the problems of cybersecurity, where you've got a continuously evolving threat. You might design a system to monitor the driver or to try and avoid a particular type of use, and people will always think of ways around it again. So I think there's only so much you can do technically, and then maybe there needs to be another framework around it as well, because we've got already at the moment, of course, Brian mentioned about we've got a driving license, we're allowed to drive, but we're only allowed to drive if we stay within the rules that are set for driving, and there are penalties if I don't follow them.
Yeah, I understand. So Paul, Prashant, Siddharth, any of you want to comment from
So I think it comes down to who's responsible for deciding what's an acceptable risk. And in the aircraft industry, you can essentially design for zero risk. So things are so unlikely they just won't happen. I mean, they may not achieve that, but you can design. You can't do that in automotive. So someone has to decide what is an acceptable risk. And arguably, that's not really the OEM's job to decide what's acceptable. They need to be told what that is an acceptable risk. And so therefore, you need to be able to understand the world, and regulators probably should have that responsibility, and also taking evidence from lots of places. But society should decide what's the acceptable risk, not someone with a lot of money.
Just jumping on the concept of the misuse aspect and people not using it properly. I think there are two aspects to it, and one is a big engineering responsibility that we as engineers have. We tend to design systems and then we say it's human error, it was misused, and that's the cause of the hazard. There is a reason for that misuse because the design was created without keeping the human in mind, and that actually the design led to the misuse itself. So I think there's a big aspect of actually having the user-centered design and including the user as part of the design making process that would prevent the misuse. So that's the engineering side of things. The other aspect, I think, on the social side, it's very important that that we start looking at communicating what is automated and what is not automated. I think the Law Commission has done a fantastic job of making it as a criminal offense of using self-driving when it's not self-driving. So that's just a first starter. But I think we need to follow up on that. And I think there's some CCAV work also happening around public awareness. So I think it's both our as engineering responsibility and the social side also.
Yeah. I sometimes use the term computer-assisted human error, which I think we often do. But Prashant, did you want to comment? Then I'd like to sort of
just something quite similar to what Siddharth was saying, right? I think the name is also not a problem. Just because we change the name to something that is more in line with what the function does, it suddenly doesn't become safe. I think it's just the human nature of when the system keeps getting good, we become complacent. So we have to do the misuse analysis and have mechanisms in place like driver monitoring and all this stuff. So to make sure that the driver is attentive and have safety mechanisms in place. So I think name is just a distraction, and we are just finding like a scapegoat with the name, I think. Yeah.
Okay, thanks. Brian, can I turn to you?
Yes, I was just going to reinforce this bright line distinction that the UK wants to introduce between ADAS and automated vehicles. They, as Siddhartha says, the UK is minded to accept the Law Commission's recommendation to have controlled terminology over some terms, but the bright line distinction is probably not fleshed out enough because it is a big social issue, and the engineering solution to a human factor is very important. I think there must be an assumption that as much as you try public education, engineering controls may be more successful than social engineering controls. And you only have to look at the fact that so few people even understand the latest major updates to the highway code now, let alone have read them to understand the whole terminology. There's a whole hierarchy of road users has changed, but you'd be lucky to grab a random driver and find out that they understand those latest changes. So whether or not something is actually even more safety critical, your vehicle is incapable of doing something, don't do it, actually gets through about something more than the vehicle simply preventing itself from being driven under certain circumstances. It is anyone's guess, frankly. As a lawyer, we can legislate, but we can't control any results.
A prominent human factor expert once said to me that human error is a symptom, not a cause.
Right. Yeah. I think that is indeed right. But actually, let me just pick up sort of one other question I think is relevant here, because sort of saying many drivers with physical impairment require approved vehicle modifications and equipment to enable them to use vehicles, including control over the vehicle when it's necessary. So the question is, how will the development and testing scenarios accommodate such needs where human interaction remains a requirement? And obviously, if we get to a really clear, fully automated driving system, that will probably at some point cease to be a requirement. But we're talking about things like ALKS, then that does indeed remain a requirement. I mean, is this something that you think we have in hand as a community, as an industry, or are there still many issues in this space we've yet to address? Sorry, Hulk, I didn't.
It's a hard one, so I'll go. Nobody once did that. I'll try that. I think there is a definite cognizance of this issue. I don't think the ecosystem has an answer as of right now about this. From a scenario-based testing perspective, I think it's yes, it's okay to say ODD-based, behavior competency-based. What we right now lack is how detailed your ODD should be, how detailed your behavior competencies should be, and that will then reflect in the rigor that you have. So I think more discussions in the ecosystem need to happen around that. Then we will be able to address some of these issues where we are able to capture some of the behavior competencies of the other people.
I will say that the law commissions did look at this, and they recommended, I keep on referring back to them, but it's because they were so comprehensive, actually. And the government has taken on board their accessibility concerns, and they're very likely to find them a way through into the authorization process. So developers who develop systems which have not been designed to be accessible and may essentially find that those count against them in securing authorizations.
Yeah, I can quite understand that. And I think a number of things like that the Law Commission did think about very deeply, or they were well advised and have been very clear. There's not so many questions coming in now, but I mean, one has come in, which I think probably I'd like to turn to Paul with first. What are the thoughts around these autonomous vehicles when and if involved in collisions? They need to get the data for investigations. I think there's a technical aspect of this, but then there's, I think, also a legal question about the accessibility of data, and there may be some IP issues around that. But Paul, did you want to lead on that?
Yeah, I mean, I think one of the, if you fill out an accident form, you sort of want to be able to talk to all the drivers. What did you think was going on? And so I think there's a case there that there should be a standard set of data that is a basic explanation of what the vehicle was intending to do, what it was aware of, and the rest of it, where you could do a pretty, a reasonable analysis of the situation and then apportion and blame. You only want to have to go back to the OEM for a really detailed analysis if you're suspicious that they really haven't done their job properly, or there's something quite unusual about the accident. But there will be cases, as autonomous vehicles become more prolific, where there's a number of accidents and they can be cleared up much more quickly in the same way as full human-to-human accidents. And if it's an awareness that there are situations where even an autonomous vehicle cannot deal with something, but it's for whatever reason it's acceptable, then that could be dealt with more clearly. So a standard set of data, and I'd argue that could be something along the lines of DCD. So what objects was it aware of? What did it think was going on? You'd be able to get to a conclusion quite quickly.
Thanks. Yes, I must admit, I'm hopeful that sort of approach would work in accident investigation. The amounts of data these vehicles can potentially generate is absolutely vast, and if that gives us a human intelligible level of abstraction of what was going on, I could imagine that actually being a very, very powerful thing to do. But I mean, Brian, what you think from a legal perspective around this? Because obviously there's talk about setting up this accident investigation branch, isn't there? Which I assume the government will go ahead with.
Yes, it is going ahead with it, although the plans haven't been set out in full yet. But largely, I agree with Paul. I mean, in theory, there will be regulation over the amount of data that these vehicles should be capturing. There will be some standardization that's going on already. But for a lawyer's point of view, it would be great to think that there was a narrative account that was ultimately produced by the data set of what happened, in which case, as lawyers do, you essentially just have to cross-examine the integrity of the said data set and the narrative account. And there will be some ethical issues around that. You know, thinking to the kind of Horizon post office scandal, and you know, the way that, you know, humans and people can be affected by the decision making fundamentally of vehicles. There are some ethical and kind of auditing requirements there to assure the legal system.
Yeah, indeed, and I think some of us think it's quite astonishing that there's still this assumption of the you know, infallibility of computer-based evidence, when I think everybody knows that that's not true. But I mean, Prashant, from a manufacturer perspective, do you see challenges around the sort of accident investigation, or do you think there's going to be ways of managing the complexity and the IP stuff?
Yeah, no, I think transparency is a key issue for trust. So if we are not transparent and we are trying to hide information, then it's bad for us, and it's bad also for the industry. So we want to put mechanisms in place which shows us why things have gone wrong, and then we learn from them. But the whole idea for us is to not be at a stage, so we want to avoid that. So we don't want to like deploy anything unless we are very confident that we have done all the things we could do, and then we deploy it and have mechanisms in place to detect when things go wrong, so that we can fix them, like the operational side of the SOTIF. But yeah, I think if we want to go into production, we have to kind of prove various things, like we have driven enough to see that we are not discovering any new unknown scenarios, and even when we do, our system more or less reacts safely. And we also have mechanisms in place to make sure that we can update our systems when we find any new safety issue. And also all the things that we already found out as unknown unsafe scenarios, they are properly tested and validated through simulation and vehicle level testing and all. So even we find it very difficult to have this comparison saying, is it as safe as a human driver and all, because it's not really quantifiable, because we are talking about maybe hundreds of millions of drivers driving all over the world and trying to compare it with maybe 1,000 vehicles or 100 vehicles. So that's really difficult for us to also comprehend and use it as a reference. So most probably what we will do is be very rigorous in our engineering process and do the best we can, and only when we have good confidence that I think this is safe and we put it on the road, we would do something like that. But once we do that, we think transparency is important, so that people trust us and also trust the industry, because even some others doing something wrong can affect all of us if people lose trust in this industry.
Absolutely, thank you. I think that's a very helpful observation. So I'm being reminded I should sort of draw things to a close. I'd just like to pick out a couple of sort of very specific points. I mean, as somebody's reminded me, you know, that the BSI standards work, there is a PAS 1882, which is at least a starting point for collecting data for accident and incident analysis, which I think is worth looking at. And the point about as safe as a human driver, certainly some of the work I was involved in, we recommended that shouldn't be used as an approval or authorization criterion, but it would be something you'd look at retrospectively as you collected data from operation. I still think that's a more realistic perspective, although whether or not the relevant minister will think that is another matter. But I'd like to draw towards the close and to thank all the presenters for what they said, some really interesting ideas, and I hope a very complementary set of perspectives which the attendees at the webinar have found useful. And thanks very much to the 5 of you for responding so well to the questions that have been posed. You never know what's going to come, and some of those are actually, I think quite challenging. So I hope you find it interesting as well as the audience getting, you know, response to those questions. So from that, I'd like to hand back to Nick to draw us to a sort of final conclusion. So Nick, over to you, sir.
Thank you, and apologies for the mood lighting I think to have on my screen. But I'd just like to echo John in saying thanks to all of our speakers for giving up their time today and for their excellent presentations and for sharing their expert views. And obviously a special thanks goes to John as well for chairing the webinar expertly. A number of the resources that we've discussed today, the BSI PAS documents, for instance, and the Flex that Siddhartha referred to, you can find them by following the web link that's on the screen, bsigroup.com/CAV. We've posted that link in the chat. There's some links there where you can find out about more webinars that we're hosting in the coming months, and also we have BSI's online standards subscription, BSI knowledge, that you can go and find out more about there. But just we'll draw to a close there, and just again to say a big thanks to everyone who's been involved today and for attending. Really insightful session. So thank you very much, and we'll close there. Goodbye.
Thank you.